Welcome to today's Explainer. We are going on a journey, quite literally, deep underground. We're going to completely demystify the Earth's physical makeup, working our way from the tiny, microscopic building blocks of the planet all the way up to massive landscape-altering structural deformations. If you've ever wondered how the ground beneath us was actually formed, or why knowing this stuff is absolutely critical for extracting the resources that power our modern world, well, you are in the exact right place. Let's get into it.
Here's our quick roadmap for today. We'll start with number 1, Earth's ingredients, the minerals. Then number 2, the 3 types of rocks. Number 3, bending Earth, faults explained. And finally, number 4, the breaking point, geological faults.
Starting off with Section 1, Earth's ingredients, the minerals.
When you look out at a massive rocky landscape and try to make sense of it all, working backward always starts right here. In geology, the word mineral has a very strict definition. It's a homogeneous, naturally occurring substance. It has definite physical properties, and, this is the most important part, a composition that can be expressed by a specific chemical formula. Think of it like a highly specific ingredient in your kitchen pantry. Just like pure table salt has a very specific chemical formula, minerals like quartz or hematite are chemical compounds with exact, unchangeable recipes. If you change that chemical makeup even a little bit, you've changed the mineral entirely.
And this brings us to a really crucial distinction. What is the actual difference between a mineral and a rock? Well, if minerals are the flour and the sugar, the pure ingredients, then rocks are the baked cake. Minerals have that incredibly strict chemical composition. Rocks, on the other hand, are just mechanical mixtures, or aggregates, of 2 or more of those minerals. They don't have a definite chemical formula of their own. Take granite, for example. Granite is a rock. It's essentially an aggregate cooked up from 3 totally separate minerals: quartz, feldspar, and mica.
Because minerals have such exact chemical makeups, they also have highly specific physical properties. Geologists use these in the field all the time to figure out what they're looking at. There are 5 main ones. First is color, though honestly that can be a bit variable. Then there's specific gravity, which is basically a measure of density. We also look at luster, which is just how light interacts with the surface. Galena, for instance, has this brilliant metallic luster. Surprisingly, taste and smell play a role too. Rock salt is instantly recognizable just by tasting it. Finally, there's streak. This is the color of the mark a mineral leaves when you drag it across an unglazed porcelain plate. Hematite, for example, always leaves a very distinct cherry red streak.
Moving right along to Section 2, 3 types of rocks. Okay, now that we've got our ingredients sorted out, let's explore how the Earth actually cooks them up. First up, igneous rocks. These form when molten material, magma, cools down from deep within the Earth. Geologists classify these using a really elegant grid system. Across the top, they're divided by their chemical composition, specifically their silica content. This ranges from acidic rocks, which have high silica, like granite, all the way down to ultra-basic rocks with low silica. Then, along the side, they're classified by texture, which is entirely based on how fast they cooled. Plutonic rocks cooled very slowly, way deep underground, creating nice, big crystals. Volcanic rocks, though, they erupted right at the surface as lava, cooled incredibly fast, and have glassy, superfine textures. And hypabyssal rocks? They just cooled at intermediate depths, somewhere in between.
Beneath the surface, these molten rock formations take on some truly fascinating shapes. Just imagine looking straight down into the crust. Way down at the bottom, you might find a massive, irregular shape called a batholith. It's a gigantic blob of magma that cooled deep underground with no known floor. Compare that to a dike, which is a vertical sheet cutting straight up through pre-existing rock layers. A dike forms when magma violently pushes up through vertical cracks and fissures. Then you have sills. These are horizontal sheets of magma that push their way sideways, right between the existing flatbeds of rock.
The other 2 major rock types are sedimentary and metamorphic. Sedimentary rocks are basically the Earth's ultimate recyclers. They're formed by the breaking up of pre-existing rocks, which are then carried away by water or wind and dumped into basins and flat layers, or beds. Sandstone and shale are your classic examples here. Metamorphic rocks, on the other hand, are the extreme survivors. These are pre-existing rocks, could be igneous, could be sedimentary, that have been fundamentally, completely altered by intense heat and crushing pressure deep within the Earth. A great example is when standard run-of-the-mill sandstone gets baked and squeezed so hard it physically morphs into super hard quartzite.
Section 3, bending Earth, faults explained.
So let's zoom out to the macro scale now. What actually happens when those vast horizontal beds of solid rock are subjected to immense, unstoppable pressure?
They behave almost like a rug being pushed together from both ends. They buckle and create folds. When the crest of a fold forms an upward arch, that's called an anticline. If you picture it, the beds slope or dip away from the center line. Conversely, if it forms a downward trough or basin shape, that's a syncline, where the beds dip inward toward the center. Geologists constantly measure this dip, the angle of that downward slope, along with its strike, which is the horizontal compass direction the rock layer runs across the actual landscape.
So what does this all mean for us? Why does a mining geologist care so much about this? Well, folds completely dictate where valuable resources are actually located. A thick coal seam might have been deposited perfectly horizontally millions of years ago, but folding will cause that whole seam to bend. If you happen to be on the top of an anticline, that coal might literally poke right out of the ground at the surface. Geologists call that an outcrop. But just a few miles down the road, if that exact same rock layer dips into a syncline, that coal seam could be plunged hundreds of meters deep underground. Understanding this geometry, knowing exactly how a seam dips and strikes, is quite literally the difference between striking it rich or just drilling a very expensive hole into useless dirt.
Finally, Section 4, Breaking Point, Geological Faults. Sometimes, the tectonic stress on the Earth is simply too massive for the rock to just elegantly bend and fold. Which brings us to a literal breaking point, a geological fault. By definition, a fault is a fracture in the rocks, usually associated with lateral or vertical displacement of those fractured beds. Faults happen when the inherent physical strength of the rocks is simply no match for the immense stress of the Earth's movements. The rock just snaps, and the two sides slide past one another.
This fracturing usually plays out in a few distinct ways. When the Earth is being pulled apart under tension, you get a normal fault. The rock breaks, and one side physically slides down the fault plane. The broken layers, or strata, pull away from each other. They don't overlap. But under intense lateral compression, when things are being violently smashed together, we get a reverse fault. Here, older rocks are literally thrust up and over the newer rocks. In a reverse fault, the broken strata actually overlap. Get this, if you were to drill a vertical hole straight down through a reverse fault, you would literally pierce the exact same layer of rock twice. Crazy, right?
For a mining operation, faults are the ultimate nightmare. They are a massive disruptor. Imagine a team of miners tunneling horizontally, happily following a rich, thick coal seam. Then, suddenly, they hit a solid wall of completely worthless rock. They've hit a fault. That vertical displacement, which geologists call the throw, means the rest of that coal seam could now be 10 meters above their heads, or it could be 50 meters below their feet. This area where the coal just vanishes is known in the industry as a want or barren ground. Figuring out where the seam went requires some incredibly precise geological mapping and a whole lot of puzzle solving.
And that wraps up our explainer for today. From the exact, rigid chemical recipes of tiny microscopic minerals to immense, continent-sized sheets of rock folding like paper and snapping under tectonic stress, our Earth is so incredibly dynamic. It really makes you wonder, the next time you step outside, what massive, ancient, hidden geological forces have folded, faulted, or thrust the deep crust right beneath your own feet? Keep that in mind and keep exploring.